Good afternoon, everyone. Hi, I'm Gerard Stewart. I'm the communications coordinator for the NFM research programme. Welcome to the 18th in our series of webinars to help researchers and practitioners share knowledge and experience in NFM. Today we've got Keith Morrison and Will Maslanka from the University of Reading. They're from the Landwise project, and they're going to be talking about improving soil moisture estimation using drones and space radar. I'll hand over to them very shortly. Just a couple of quick housekeeping issues. Please, to avoid distractions, keep your video and microphones off. Please do ask questions using the chat function. If you click on the speech bubble, that will give you access to that. And so Will is going to be presenting, but Keith's manning the chat function, so he'll be there and able to answer questions as the webinar proceeds. We are recording the webinar, and I'll make it available, I hope, later today via our website, and I'll post a link in the chat to that shortly. So the Landwise project, of which Keith and Will are working on, is part of a 4-year NERC-funded £4 million research programme. Alongside 2 other projects. So we're carrying out novel science to improve the understanding of natural flood management, where possible, including quantification. We're looking at a range of NFM measures in different types of catchments, flooding scenarios, and at different scales. And with the overall aim to improve evidence and understanding for policymakers and practitioners. So yes, there's 3 projects listed there. Each have their own website, and you can link through to them from our program website. They're in different parts, focusing on different parts of the country, and looking at different aspects of NFM. The program, the research program, it really is, it's a collaborative, very much a collaborative piece of work, and the involvement of partners in this work is critical to its success, and of course the uptake of the recommendations that we are working towards. And really this webinar program is part of that collaborative approach. So yeah, we're hoping to share and really build an NFM community through our work, or contribute to that at least. So that's enough from me. I'll hand over to Will.
Cool, thank you very much, Gerard. I'll go and share my screen now. There we go. Can you confirm you see that?
I can't yet. It might be because I'm still in viewing my slide.
Ah, okay.
Can other people?
Yes.
Good.
Yes.
Okay. Good. Yeah.
Perfect. Right. Well, then I guess that's a good place to begin. So, hi everyone. I'm Will Maslanka. I'm going to be presenting the webinar today on improving soil moisture estimation using space radar. This work is part of as Gerard said, as part of the Landwise project, and I've been working closely with both Keith Morrison and Dr. Kevin White, both of which at the University of Reading. The presentation as a whole, I'm going to kind of give it a brief outline now. I'm going to start by introducing or reintroducing a bit more about the Landwise project, and specifically about the place of remote sensing within the Landwise project. I'm going to go through a little bit about the concept of space-based radar remote sensing with respect to soil moisture. And then I'm going to go through some examples of the work that I've been doing within the Thames Basin using the Sentinel-1 satellite constellation on both the catchment and on basin scale. And then I'm going to move down onto the field scale, and I'm going to talk about how the satellite-based work relates to some of the NFM work that we're going to be doing, especially with respect to some of the field data that we're going to be collecting, hopefully very soon. So I'm going to start off first with an introduction to the Landwise project. So Landwise stands for Land Management in Lowland Catchments for Integrated Flood Risk Reduction. I've bolded the letters of Landwise because the project acronyms always make me laugh about where you're able to go and throw the letters in. And it's got quite a few overarching research questions as a whole. It's effectively going to be looking at how different types of land-based NFM measures, how they work and how they are at increasing the infiltration, evaporative losses and below groundwater storage in different locations across the lowland catchments. We're going to look at how that effectiveness, how it varies and how it varies seasonally and between years with respect to antecedent conditions, precipitation, magnitude and duration, and then see how effective these land-based measures are at delivering catchment-wide water storage and infiltration measures and reducing runoff rates. Now, these are quite wordy questions, so I like to think myself, I like to simplify things down. So simplified, we're basically going to be looking at how effective different land-based NFM measures are at keeping water out the river, how that effectiveness varies, and how effective they are at reducing the flood risk across different catchment scales. Now, with a large university project like this, it's split into a number of different work packages so that different people can focus on different areas. There was a talk back in, it would have been March last year, by Chris Short and Angie Elwin. They gave a talk about the Landwise project with respect to work package 1, so using local knowledge and technical data to create scenarios, where they were doing workshops with farmers and landowners to talk about different types of NFM measures they'd like to see. The work that I'm basing in is within work package 3. So we'll be making measurements from remote sensing data using satellite models. And this is a lot of my satellite-based work, whereas I'm also have a little bit of overlap with work package 2, which is where we make measurements in the field. So we'll be going out into the field and collecting measurements. The data from work packages 1, 2, and 3 all get fed into the modeling work package, which is work package 4, and this is where they're going to be doing the bulk of the modeling for how different NFM measures work and how effective they are, and doing slight tweaks to them, how that would impact the effectiveness. So that's a little bit on Landwise. I'm going to talk a little bit about radar, as that's the crux of the work that I've been dealing with. So I'm going to go through a little bit of the basics of how radar works, and I'm going to apologize to anybody who already knows how it works, but it's quite good to have a refresher every so often. In its simplest terms, radar works by having a transmitter and a receiver. The radar unit would transmit a signal, so this would be a pack of electromagnetic waves that would then effectively bounce and scatter off of a object, off of a target, and then we were able to measure the return of the signal and have a look to see how the power varies between the signal that we sent out and the signal that we receive. And we can then have a look at this echo, or we call it the backscatter, or sigma naught. And that's a measure of the return signal. And this gets used in a variety of different ways, in a variety of different applications. So speed of a moving car is used by a radar gun used by the police. Radar is used for detecting aircraft, so things that are like Heathrow and Gatwick will have their radar towers where they're able to go and detect where nearby aircraft are. The Met Office use it for rainfall and for snowfall precipitation events. But in the case of Landwise and with our satellite-based radar schemes, we can point them at the ground and then we can get measurements of soil moisture from there. So a little bit of theory of how that works, and it's going to be one of the few bits of theory in this, so I'm going to keep it quite brief. The water in the soil affects something called the dielectric constant of the soil, which is effectively kind of the electrical properties of the soil, and is very much how it kind of influences the amount of signal that is returned by the radar and how much is received by the radar. The amount of water in the soil really impacts this dielectric constant, and in turn influences the intensity of the radar backscatter coefficients, this sigma naught. So by measuring sigma naught over a extended time period, we can estimate a relative soil moisture as long as we've got a wet and a dry reference. So we can do this by looking at a time series, looking at the largest to smallest values in the time series, equate those to the wettest and driest, and then can scale the rest of the time series towards that. This is something that we're going to be doing, or I'm going to be showing with my satellite-based stuff over the time series. I believe I'm going from October 2015 to January 2021. If we measure the backscatter and we have a surface roughness measurement at that time, so this is much more difficult with satellite data, we're able to estimate an absolute soil moisture. So this is done by having a look at the backscatter, having a look at the surface roughness, and using a backscatter model to estimate the amount of the soil moisture and the amount of water in the soil at that time. The satellite that I'm going to be using, going to be displaying and talking about today is Sentinel-1. That's at the moment, it's a 2 satellite-based constellation. The satellite 1A was launched in 2014 and the second was launched in 2016. Between the 2 satellite constellation, it has a strict 6-day repeating cycle. So this is where every 6 days is when it completes all of its orbits. And within each cycle, there is 175 individual orbits. So the 2 satellites are both doing 175 orbits every 6 days. Now, these satellites have got a very dependable viewing geometry and spatial coverage. So we're able to know if it's a specific orbit, we'll know exactly where it is and what is the spatial area that it's looking at. And this is very good for when we're doing some of our soil moisture estimation, because we can filter the number of orbits that we want, and we can have a look and say specifically, okay, I want to look at this orbit in this area, and we'll know that it is pretty much almost an identical spatial coverage. There's a slight variation, but that comes up in some of the processing that I'm going to talk about later. It's the frequency, I should state that the frequency that it uses is 5.4 gigahertz, and its multi-looked resolution is 20 by 22 meters. So having a look at the pixels, each pixel covers a 20 by 22 meter area. So we can cover a large area of the Earth in its swaths and looking at its resolution. So as I've said, that we're kind of looking at as I mentioned, we're kind of looking at parts of the Thames Basin. So this is a brief, kind of a very basic image showing the coverage. Oh, hello, kitty. Sorry about that. Oh, nope, you don't want to be in the webinar. Sorry, the cat went to the vet yesterday, which was wearing a nice red t-shirt. The orbits. This plot shows the number of orbits that passes over the UK. So this is the number of orbits for Sentinel-1 during 2018, where the nice beigey yellow color is 245, and then the deep blues are 100. We've got some of the Thames subcatchments, so like the likes of the Loddon, the Kennet, and the Pang, all highlighted there in black, and we can see that they're in a nice diagonal of yellow, showing that they've got quite a high number of orbits over 2018, and they've got quite a nice coverage. So specifically for these, it covers orbits 30, 81, 132, and 154. So we've got these nice 4 orbits that cover these I think it's every 6 days there's 4 orbits that covers it, which is fantastic. Oh, no, you're just going to be involved in it. These orbits can be split into 2 separate categories. We've got both the ascending orbits and descending orbits, which we're able to then kind of filter them in by either ascending or descending, just in order to keep the file size and the file quantity to a manageable level so that we don't get bogged down in some of the processing. So for this work, I'm just going to be showing the orbits 30 and orbits 132. So specifically, we're going to be looking at the overlap between orbits 30 and 132. So that ends up being this kind of nice greeny area in between the two, which is this kind of black boxed area, which we can see nice and clearly here, where the red and the blue triangles within that black box is the data that we're cutting out. So unfortunately, you can't just download and use the Sentinel-1 data in its normal format, there's some processing that has to go in the background. I'm not going to go into the details of that specifically because it's really dull, but I'm following the processes laid out by Faponi 2019, and this is kind of a standard process of of fixing the orbit, removing some of the noise, removing the border, and this sort of thing. Once you've gone through this kind of this processing workflow, you'll end up with images like this. So this is a scan for the 11th of September in 2018. This is Sentinel-1A orbit 132 using the VV polarization. And we can see here that you've got the catchments here are shown in red, and you've got the nice scale in backscatter from white to black. And you can begin to make out, if I just show I want the laser pointer here, you can quite clearly make out some of the major settlements in this area. So you've got this nice white, brighter patch here in the Upper Thames. This is Swindon. You can begin to make out Oxford over here. And then you can also just make out Reading between the Kennet and the Loddon here. So I'm somewhere sat in here. The larger backscatter values or the larger magnitude are in white with the darker in black. So because standing water doesn't have produces much lower returns, you can also make out some standing water bodies. So you've got over here, this area here in the Upper Thames is the Cotswold Water Park. So you can quite hear from in this kind of multi-look native resolution, you can see quite a clear number of things. Unfortunately, from this one image, you can't get a measure of soil moisture because you need to have a time series to compare them all against. So let me make sure that I'm in the right zone here. Yep. I want to. Sorry, the cat's just hit something. I just want to make sure that I'm back on the right thing. There we go. Get rid of the laser pointer. Cool. So you get images like this. So as I said, we want to have a time series so that we can look at this. So if we were to do repeat measurements of this and take every scan from orbits 30 and 132, we can compare a single scan. So I call them scenes or snapshots. We can compare them against the largest and smallest backscatter values, assuming that they correspond to the driest and wettest backscatter for soil values, respectively. Now, in reality, we don't actually use the largest and smallest because they would introduce outliers and introduce errors, but we use a statistical method to remove these outliers. So we end up using about the 5th and 95th percentile rather than the largest and smallest values. So knowing that, we can use a simple formula to estimate a relative soil moisture. Now, this is a well-defined method, as it was originally done for the ERS scatterometer by Wagner in 1999. It's also been done for the ASCAT satellite instrument and this satellite platform, and then has been updated as well for Sentinel-1 by Hornack et al. 2012. So the model here is shown below, but to make it as a nice simple formula, I'm just going to change it around. It's effectively an index comparing the snapshot compared to the dry backscatter and the wet backscatter. But what this does is we're able to turn backscatter images like this. So this is that same one from before for the 11th September 2018. We compare the backscatter values, comparing that to the wet and dry thresholds, to images like this, where we have orange is particularly dry and purple is very wet, relative surface soil moisture. And we can make out this nice kind of wet soil area that's running through the Kennet, the Kennet, the Pang, and I believe that's like the Chilterns area, with the Loddon being particularly, and the Loddon and the upper part of the Upper Thames being particularly dry. Now, while I've been saying that all this stuff is in the original resolution, so there's 20 by 22 meters, you shouldn't really do the soil moisture observations and soil moisture estimates at this resolution because there's other things that impact the backscatter. So for things like the vegetation, the say crops and things that come up, the water content in the vegetation, the orientation of how the crops have been planted, the size of the crops, the amount of crops that have been plotted, the crop density, and even things like wind and how the crops are bending in the wind can affect the backscatter values. And then with the soil, as I mentioned before, the soil roughness has an impact. If the soil has been, how it's been, the tillage of it kind of makes an impact, as well as the soil moisture. So one way to kind of get rid of a lot or mitigate a lot of the impacts, especially from the vegetation, is to do some spatial averaging so that you can mitigate this impact from pretty much everything but the soil moisture. So if we have our original resolution plot, so this is our 20 by 22 meter, one of the averaging that is quite common, especially in the literature and in some soil moisture studies, is a 1 kilometer resolution. So this is averaged over, so now each pixel is a 1 kilometer by 1 kilometer. You can still make out this quite strong soil moisture, or this like wet soil moisture pattern. But because we're working, or we've started with the original resolution, we can then alter how this averaging works. So we've got the 1 kilometer here. We can go to 500 meter resolution here, 250 meter resolution, or even down to 100 meter resolution. So we can really make out these patterns and this moist relative surface soil moisture pattern across the Kennet and the Pang and this sort of area. So I've talked a lot about how I've made these measurements and specifically the scene, but haven't really addressed why there's this surface soil moisture pattern here. And it's the 11th of September 2018. There's been no real particular flooding in this area, so it's not any kind of fluvial impacts. It turns out in this instance, it's a localized shower passing over the area. So I've gone and grabbed the Met Office radar precipitation data and overlaying a 3-hour accumulation. And you can see that if I flip between the two, it overlays quite well and showing that the 3-hour rainfall has worked quite well in this instance and shows that it really is the precipitation that's being the main impact here and the main driver for this surface soil moisture. So this has all been for a single scan and for one single image in time. But I've been talking about having it as a time series. So here I've got the spatial distribution of each scan for the Kennet catchment. That's plotted at the top with the same color palette, so purple being 100% relative surface soil moisture, and orange, that deep orange brown being 0%. And then on the bottom of the plot, I've got a kind of the average of the Kennet. The black line shows the average of that single scan, where the red line is a 5-scene moving average. So I'm taking, at any given point, I'm taking that scene, 2 scenes behind it, 2 scenes ahead of it, and averaging it. And it's acting as a smoothing, it's kind of displaying a smooth plot. Now, I'm only really showing the Kennet in this instance, just for display purposes. I could do this for any catchment that I've got within my scan. If I wanted to have a look at other catchments that aren't in my area of interest, I could reapply the processing data, re-download the data, reapply the processing, reapply the work, and get other catchments. So it is quite a robust method of working. And this, I mean, I'm going to take this time while the animation is running, and we're kind of going through and seeing how as time progresses, the soil becomes more moist and then dries out. I'm going to say that this is the sort of data that's going to be passed along to work package 4, which is the modelers within Landwise, because this is the antecedent conditions that they will be needing to know for how quickly the soil gets wet and dries up. And it kind of provides the real world soil moisture data to them, especially on this like catchment and basin-wise scale. So we can, now that we've gone through 2 years worth of data here, we can begin to see the kind of the annual cycle of soil moisture increasing over the winter before decreasing into the spring and the summer. At this point here, you can really see the soil moisture really drop out from comparing between April 2018 up until about August, September 2018. This is because of the kind of drought that happened and the prolonged period of no rain, which really dried out the Kennet and dried out large areas of the Thames Basin. It will also, as it kind of filters through, you can begin to see it moisten up and get an increased soil moisture over the winter. And once we get to it, I'm going to say to pick out, to watch out for the winter of 2019-2020, because this is when there was a large number of flooding events in the Thames Basin, and especially along the Kennet. I remember the parts of the Kennet that runs through Reading and part of the Riverside shopping complex was all closed because the Kennet and some of the canals burst their banks. So I'm just going to take this time to just have a quick drink of water. So yeah, so if we compare, say here, just the 2018 summer to the 2017 summer, you can really see that the soil moisture is much lower in that 2018 period, which is kind of would make sense compared to how dry that 2018 summer was in comparison to, say, 2017 or the 2016 period. I think the 2019 summer was, again, it was drier, not as dry as the 2018 one, and it wasn't quite for such a prolonged time. So here we're seeing you can see some of the instances where the Kennet is really flashing in that deep purple, where there's some really high soil moisture areas, and this is between in the winter, the beginning of 2020, when there was a lot of the flooding instances. And again, now we get into April 2020, we begin to see it really drop out again as the soil begins to dry up. So I'm just going to let the animation filter through to the end before I move on to the next slide bit, because while this is showing this data in the time series at each scan, there's still a little bit of analysis that needs to be done just to effectively ground truth the data to make sure that where the instances that we say that the soil is wet or is dry, that is actually occurring. So this will come through now to the winter of 2020. There we go. So that's the completed time series, which is, you can see at the bottom. As I was saying about kind of the ground truthing of the data, if we look at the Kennet plot at the top, we can see that it looks like it's relatively dry. And I'll actually highlight that it's at this point here. So it's the 3rd of March, 2018. Now, it's this especially this scan and this snapshot is particularly interesting because it's much drier than the other scans on either side of it, either from the couple of scans before or the couple of scans afterwards. And this isn't an instance about the fact that the soil suddenly dried up over the course of a couple of days and then got wet, but it's more the fact that this is during the Beast from the East in 2018. And this is actually highlighting there's snow over parts of the Kennet. Now, because there's now snow overlying, we're unable to see the soil, and how we're dealing with frozen soil and frozen water. This has its own interesting impact on radar data and radar backscatter, which effectively plays havoc. So in normal kind of display purposes, or while I'm doing analysis, I would normally remove this scan because it would provide an anomalous data. But in this instance, and this for display purposes, I'm keeping it in just to highlight that and really stress that even with doing the analysis, you still have to kind of ground truth a bit of the data. So that's looking at the time series, and it seems that it's having so much work has gone into what was maybe a 1.5-minute animation. It really doesn't really do the justice of how much work has gone into the background and behind the scenes sort of thing. But with these time series complete, we can look at how the soil moisture changes with time, especially with respect to different land properties and soil properties. I'm not really going to go into the specifics of exactly how the soil moisture changes with respect to the different land use types, because that work is still ongoing, it's still preliminary, and we haven't got to the fieldwork stage where we're really going to hammer down on this. But on the kind of catchment and basin scale soil moisture, we can go into, so here using the Kennet, this is a snapshot for the shower that I showed before. We can have a look and see how the time series the soil moisture changes with respect to land use. So this is the Centre for Ecology and Hydrology's Land Cover Map 2015 model, where I've taken all of their woodlands and amalgamated them together, taken all the grassland, amalgamated it together. But we could have a look at the time series and filter out everything that isn't grassland and see how that would compare. We could also compare it to different soil properties. So this is the Cranfield Soilscapes data with specifically the drainage properties for the Kennet. And we can have a look to see how the soil moisture would depend on how the soil moisture changes depend on or compare in the freely draining or compared to the impeded drainage areas and that sort of things. Now, this has all been satellite based and broad scale and catchment scale things, but NFM can be quite important on the field scale and on a much smaller basis. So kind of how is this satellite work going to really work and this radar work going to really work with that sort of thing? And this is where this kind of satellite-based stuff goes back into our NFM and the land-based NFM products. So just reiterating and refreshing the first two kind of simplified research questions of how effective the different land-based NFM measures are at keeping the water out of the river and how that effectiveness varies. The satellite data that we've got, or that I show, kind of provides the data that goes into how that effectiveness varies, of providing the antecedent soil moisture conditions, and we can begin to show different precipitation events. But how effective the different land-based NFM measures, and specifically for us, different soil-based NFM measures and different farming practices based, how effective that works, that's going to be involved into a detailed field survey that is going to be taking place relatively soon, hopefully. And that field survey, we're aiming to then better characterize the field scale heterogeneity, different practices and different soil parameters. So in this instance, we're going to be taking soil moisture observations or absolute soil moisture observations using a ground-based radar unit. So a similar piece of instrumentation compared to that's on the on Sentinel-1, but at a slightly different frequency. And because it's much closer to the ground, we'll have a much higher resolution data. So rather than having each pixel being at 20 by 22 meters, the pixels will be on a more centimeter millimeter scale. So should be much greater resolution and should be much better at getting absolute soil moisture. We're going to be doing these ground-based radar unit measurements. We're going to be comparing those to handheld soil moisture observations using a theta probe, comparisons with a piece of kit called the electrical resistivity tomography, or an ERT. And this is done by putting probes into the ground and then running a current between each probe and measuring the resistivity between those, and from that inferring soil moisture. And then we'll be comparing all of that with soil parameters collected by CEH, by the Centre of Ecology and Hydrology. And this is where we're linking in with the work package 2 from the Landwise project. So I'd said that we're talking about the soil moisture observations using a ground-based radar. This is our ground-based radar. This is our rig-mounted radar unit, or we call it the radar rig, just for short. It covers a range of frequencies, so from 4 to 8 gigahertz. So if we remember, the Sentinel-1 covers 5.4 gigs. So this, we are able to cover both. We're able to cover the range of them, including the Sentinel-1 frequency. So we'll be able to look at our data and compare that data to that of Sentinel-1 and see how they compare. We can have a look at our scans and do multiple transects across fields, highlight and aligned with the ERT and theta probes and the soil property observations. And we can have a look at those and compare them to the pixels in the Sentinel-1 data to see what sort of data is the dominant influence within the Sentinel-1 pixel. So we can have a look and take multiple observations. We can look at various different measurements. So we can looking across trafficked and non-trafficked areas. We can look at tram lines. We can have a look at areas near the fences and near gates, so we can have a look to see where the ground has been more compacted, to have a look how the soil moisture varies there in comparison to in the middle of the field. We're going to be doing a lot of different observations, and not just in observations in a single field, but we'll be looking and assessing them at different land and property types and how that affects the soil moisture in different fields in different areas and different geologies. So we're going to be comparing floodplain grasslands and floodplain woodland areas. So this is somewhere near Oxford. We're going to go and have a look and take measurements of in the woodland and in the grassland and have a look and compare to see how the soil moisture varies there. We're going to have a look at some controlled traffic compared to some conventional traffic on some chalk and clay soils. So we're going to have a look to see how that will vary and have a look at the different transects and different tram lines and infield compared to the edge of the field areas, how that works. And we're going to have a look at some of the herbal lays versus ryegrasses. We're doing that somewhere in the Cotswolds, so we're going to go and have a look to see how all that sort of things, different impacts. So some really interesting things. We're going to coincide them with the Sentinel-1 passes, so we can have a look to see how our field observations, how they compare to the Sentinel-1 observations. And we can see how we can scale up our field scale observations and see how that compares. Now, it wouldn't be a webinar in 2020, 2021 without mentioning COVID. This fieldwork data and this fieldwork stuff has been really heavily impacted by COVID, so we've not yet started it, but the fieldwork's now beginning to pick up pace. So watch this space, and hopefully in the next couple of months, I'll be able to come up with some data or some presentations saying this is how our fieldwork data is lining up, how our observations are going. So in summary, I've introduced or reintroduced the Landwise project. I've talked about how our space-based radar remote sensing works, given a little bit of theory about that. I've talked about the soil moisture data that we've collected in the Thames Basin and had a look at the time series there and talked about the different things that we can do with that data. And I've also briefly touched upon the elements from work package 3 with the long-awaited Landwise detailed fieldwork and how there's some of the work that we're aiming to do with that. So with that, I'm going to leave you with a nice false colour image of the Cotswold Wildlife Park at Cricklade, and thank you all for listening and ask if there's any questions.
Hi, Will. Thanks very much. Yes, I've got my mic on. Yeah, Keith's been busy answering questions that have come in, but we have had people did submit some before the webinar when they signed up to it, so I can ask you some of those. And yeah, please do ask questions in the chat, and either Keith and or Will can respond. So yeah, one question we had, Will, was can you explain how you chose the processes, tools you used, and their relative strengths and weaknesses?
Certainly. So the work that I've been doing, rather than trying to run everything through a single GIS platform, there's some bespoke software, especially for the Sentinel-1 data, that is done by was produced by ESA, so the European Space Agency, that's specifically designed for dealing with satellite data and for doing the processing that I showed before. You're able to do a lot of the processing there to get it from the kind of downloadable data input to a more usable data, a more usable data format at the end of it. So that's one of the kind of the main bulk of where a lot of the processing has happened. There's also, once you have it into that sort of processed output, you can feed it into any kind of programming language. So I predominantly have used the MATLAB programming language to do some of the analysis and do some of the normalization and some of the other tweaks that need to be done before, and some of the producing a lot of those spatial averaging before feeding it back into the kind of ArcGIS, QGIS programs to feed into those to do some of the spatial analysis. Personally, I prefer QGIS as kind of a platform to use in that instance, just because I feel it's a bit more user friendly, and I have a habit of crashing ArcGIS. But I feel that QGIS is a bit more of an easier platform to use, and it's a bit easier with some of the projection stuff, which has been a little bit tricky, especially with trying to get the northings and eastings and latitude and longitude to line up with some of the various different data formats that we've been using.
Okay, thanks very much. Another question was, how have you factored in vegetation growth impacts?
So the vegetation growth that comes in, as part of the processing kind of workflow. Once you get to this kind of outflow, the output bit, once you've done all of the calibration and some of the filtering, you've gone through all of that. There's an additional step of making sure that the look angle of the satellite is consistent throughout, and as part of that, kind of making sure that that look angle is the same look angle across the entire scene, you're able to do a kind of a monthly check and have a kind of a monthly normalization factor that takes into account the kind of how the vegetation has grown, because you're not going to have as much, especially over some of the farmland, you may have a lot more bare soil over the winter months than compared to the summer months. So by doing this monthly normalization factor, you can kind of take into account some of the vegetation growth and the varying slightly different vegetation types, and kind of involve that and add that in, and then kind of assume that once that has been done, it's kind of taken into account, then the real variation that comes in the varying different backscatter things are the soil moisture variances and soil moisture differences.
Okay, thanks very much. Another question was, how frequently does the satellite update the soil moisture data?
So from Sentinel-1, because it's got the 2 satellites, if you were to look into when there's going to be a certain satellite there's a repeating orbit, that orbit would repeat so if you're looking at just one satellite, it repeats a thing every 12 days. If you look at the 2 satellites, it repeats every 12 days. But if you're looking at a place, like, for example, if you wanted to have a look at the Loddon and have a look to see how often there was an overpass of the Loddon, it works out that it's about 4 scans or 4 orbits every 6 days, as it works out. There are other satellite platforms, and there's other different types of remote sensing that will have that has a slightly different like orbital frequency. But for Sentinel-1, that it's if you were to look at the Loddon, there's probably 4 scans every 6 days. How much that satellite or how much that data is updated, it's usually the kind of data access stuff that is updated is almost weekly. There's a bit of processing, and then it's almost like the last fortnight's data is released. Like the data you get now was from 2 weeks ago, and updates like that.
Okay, thank you. How accessible is the data you've used for this work?
So the Sentinel-1 data in its input format is quite easily accessible. There's a number of different places that you can download the data from. You can get it from the main, like ESA Copernicus, which is the kind of the main platform. You can download that data there. There's a number of different places like web services where it's stored, and that's where you can really get that raw data, or the input data on the raw data in all its different formats. You can get it from there. There's a number of different products that use similar or use like a similar method or use similar platforms, so different satellite platforms. These are also quite easily downloadable and easily accessed as well. So there's a lot of it is a lot of things that you need to go and access, send a form off to say that what you're going to be using the data for, and then you're able to download it. It is quite data intensive. It's quite a lot of data. If you're wanting to download all of the data for a certain area, they're quite large file sizes. So this is one of the reasons why I really looked at only 2 orbits, because it got ridiculous quite quickly when trying to look at more orbits, and it really impacted on the processing time. But it is a matter of having a look and knowing how to download it, but it is quite readily accessible.
Okay, thanks. Well, Mark Allett asked a follow-up question, which actually was kind of a more detailed version of the next one I was going to ask, really, which was, how can your work inform future agricultural practice? So linking it to the previous question, how that data and analysis, how can you actually influence how farmers make choices about land use and uptake of NFM?
So, well, hopefully that's what some of the our fieldwork data is really going to hone down on, the different types of the impacts of different farming practices upon the kind of water retention and that sort of information. On this satellite stuff, it's it gets tricky when you're looking at specific, if you were looking at an individual field, say, just because of the various different influencing factors in that kind of 20 by 22 meter resolution. A lot of what I would say is the more easily accessible data for this sort of things, you can get it on that 1 kilometer resolution, but that doesn't really help. I don't believe that's going to particularly help like practitioners as such, because it's averaged over such a large area that you can't really impact and find specific areas where they're going to be able to be impacted. Looking at some of the more finer resolutions, so maybe the 250 meter, 100 meter resolution, I feel that could be, if there was, this is something that we're hoping, maybe potentially looking at some of the stuff with Work Package 5. So this is you developing web tools and developing tools for this in this instance, where we'll be able to have the kind of some of the data saved, where you're able to flick through and see at different resolutions and have a look and see how the soil moisture changes, and you can potentially even impact to see, okay, I'll have a look to see why the soil moisture was so bad for a individual year. Say, especially with the 2018 for the drought, you'll be able to see, okay, well, I know that the soil moisture was particularly, or the retention was particularly bad that year. We know that there wasn't that much precipitation in that summer, and you can have a look and have the data that really backs it up.
Okay, thank you. There's a question. So can you get enough spatial discrimination to identify the impact of differences in soil moisture for specific NFM measures on the ground, or for groups of NFM measures?
So specifically on different types, it will be this kind of soil moisture stuff is going to be really useful for the out of river NFM measures. So they're very much these land-based stuff. I think that looking at potentially the 100 meter, that more 100 meter, 250 meter resolution, that will be much more. You may be able to get the spatial resolution there, especially looking at if you're looking at areas, especially with the land types. If you're changing a farming practice, if you're going to from a kind of conventional farming practice to a more apologies, my farming knowledge isn't particularly great, so I may go and put my foot in my mouth here, but some of the going from like a conventional one to a more modern NFM friendly measure, you may not get it at that 1 kilometer resolution or the 500 meter resolution, but that 250, 100 meter resolution, I think you'd be able to pick up some things to come from there.
Okay, thank you. There's a question which I think Anne Verhoff has answered, but I don't know if you want to add anything. I'll read out the question and her answer. So, due to accelerating climate change, are you able to find ready acceptance of necessary actions which need to be taken by Thames Valley farmers and the costs involved? And Anne responded, the plots field scale modelling in Work Package 4, which is part of the Landwise project, can also help with it. Maybe you can explain what that
Sorry,
is.
Jared, thank you. Yes, no, what I meant was actually answering the previous question, and then I think
sorry.
Dick and I touched the send button at the same time, so I meant to help out Will with the previous question.
Okay, did you want to add anything more to that? Because a lot of people won't know what Work Package 4 is.
No, sorry. So Will did mention that earlier on. So Work Package 4 is the modeling work package. So we have a catchment-scale model. So Maleki is running this for us. This is the SWOT model with a T at the end. But we're also planning to do more plot to field scale model run. So these are soil physical or even agricultural models, one could call them. So that we could look at more local effects of changes of, for example, crop type or crop rotation or soil management and so on. So we can certainly look at these more small scale NFM effects.
And if you want to find out more about that, there's a webinar which Anne and Maleki and others in the team are giving on the 29th of July. So you can sign up via the link I sent earlier. I think Joe Clark may have mentioned that already. Well, oh, hang on, we've got one here. You seem to have chosen the Upper Thames Valley due to satellite coverage quality. Are there significant areas of England where the cover is too poor for this approach to be useful?
I don't think there are areas where for the UK. So the satellite one, the Sentinel one coverage over Europe is particularly good. I mean, I feel that's because that's mainly it's an ESA project, or it's an ESA funded thing. So I don't think there's anywhere within like Upper England, or say north of England, or various parts of the UK that has got where it's sufficiently poor. I think there are some places where there may be fewer orbits, but I think that this method would still be valid. It may just be that there are less time steps in the time series, but you could have a look to vary where your where the orbits that you're choosing. So I've here the reason why I've picked the 2 orbits, or that we had looked at those 4 orbits, is because whenever we were looking at trying to find a single orbit to use, we were cutting out different bits of the catchment. I think originally we're looking at orbits 81, which covered everything other than the upper part of the Loddon, which is quite interesting because there's the geological change between this kind of a clay, or say clay to chalk, I think. So having a look at different parts of the UK, this method should still be valid, I feel. I just want to very quickly go back to that first one about the accelerating climate change. I think that there has been some of the, so as part of Landwise, we've got workshops where we are dealing with the farmers, and this is the stuff that was done by Chris Short and Angie Elwyn. And I think they've had quite a interesting uptake with landowners and farmers to have a look to talk about NFM measures. I can't say specifically about due to the accelerating climate change, but I think that a number of the farmers are quite interested in NFM and what they can do, and what impacts they can have, and how they can help, sort of thing. So I think there is still there is definitely an interest in this area. Sorry, Jared.
No, thank you, for expanding on that. And I think you have covered this to some largely, but perhaps not quite from this angle. It's how can a project make use of this technology? You've talked about the data and outputs, but maybe not quite so much the technology.
The satellite one, or the satellite, you call it satellite one, the Sentinel one and satellite observations, they'd be very useful for a number of different projects in a number of different fields. If you'll excuse the pun on NFM and fields. How can a project make use of this technology? You can have a look into various different places around the world. You can have a look in different soil moisture. This method, for the majority of places, this method is quite valid. It's very good at having a look and seeing what has happened previously. With this method is not very good at providing a forecast, so we wouldn't be able to have a look at this, use this data and have a look to see and estimate. Okay, so I think it's going to be like this in a month's time, a year's time, 10 years time. But it's good at having a look at the antecedent conditions and having a look to see how things have happened in the past. And then that sort of data would really be fed into the modelling. So as Anna said, that the effects of climate change can simulate with the model. So this is really we can provide some of the driving data that goes into bringing some of these models and this sort of things up to speed and ready to then run them forward for forecast models.
Thank you. You're just keeping ahead of the questions coming in. Are you able to take several decade time series to predict serious emergencies like the Pangbourne flooding and risk to the Thames barrier, etc.?
So the Sentinel-1 data, there isn't the time to have a look at that. You haven't got decades time series of Sentinel-1. You have it for other satellites, but you haven't with Sentinel-1. Some of the other sort of satellite data that gets fed into various other different types of forecast models and climate models, so you can go and begin to predict these sorts of factors. So this is the sort of things that you'll see the IPCC forecasts for the big climate change models, and these sorts of things that get that you see every so often. The things when we talk about the at COP which is the big climate change program. These sorts of models would be able to. The data, the work that I'm doing, you can't have a look to predict emergencies, specifically to things like in the Pang or this sort of area, because it's only looking at things that have happened in the past and we're not running anything forward. There are, flood forecasting and flood modeling is particularly difficult. It's one that's especially, I know that Anne has mentioned Maleki, who's one of the researchers in Work Package 4. I know he's pulled his hair out trying to model parts of the Pang. I know that that's a parts of it. Modeling and the flood modeling is particularly tricky. So, depending on your scale of model and what you're aiming to look at, you can try to have a look at these sorts of things. The work that I've been doing isn't geared up for looking at this sort of stuff. It isn't looking into the future and looking at flooding impacts in the future. We're just looking at the soil moisture time series of the past and then feeding that to the models.
Thanks, Will. Well, great timing, because you've answered all the questions and with some help from Keith during the
fantastic
webinar. So I'll just sum up with, or well, I won't sum up. I'll just conclude. So yes, can you see my slide?
Not yet.
Oh, there we go. Does that come up? No. No. Okay. Well, I'll just tell you. For some reason it's not showing. So yeah, thanks very much, Will, and to Keith, and for Anne as well for answering questions. Thanks everyone for attending. I hope you found that useful. The recording will be available on our website, and I've included a link in the chat to that. If you do have questions for Will or Keith, you can get in touch via the link on our website, or via their email addresses, which I'll provide on alongside the recording on the website. The next webinar is on the 21st of May, and Dr. Mark Wilkinson from the James Hutton Institute will be talking about catchment hydrology and NFM. You've got a link to sign up to that. Hope you'll join us for it. And also, if you'd like to receive our newsletter, we promise not to block up your email box too often, but it's every 3 or so months we send a newsletter updating you on the research and news from partners as well. If you do sign up, then we'll also update you on upcoming webinars. So thanks again to Will, Keith, and the cameo appearance from Will's cat, and hope you will join us again for the next webinar. So good afternoon, everyone.